Welcome again to electrostatic field. The topic of this presentation is electrostatic potential. This is our learning map. We have already discussed the laws of electrostatics. We have already discussed the divergence. We have already discussed also electric force, field, flux, density, as well as electrostatic energy. And this time we are discussing electrostatic potential. So what is electrostatic potential? Simply, it is the electrostatic energy required to move a unit charge from one point to another point by the electric field, or we can write mathematically or in equation form as V equal to W over Q. Last time we discussed that W is simply defined as minus Q integration from starting point P to end point A for dl of the electric field. If we divide these quantities, we get that VAB equal to minus integration from B to A E dot dl, which is simply the electrostatic potential between 2 points A and P. It is measured with Joule, which is a static energy and over the column. And later we'll understand this is just the volt. This is a fast memory for you. The infinitesimal lengths can be calculated for various coordinate systems as shown. Let's calculate the electrostatic potential due to a point charge. A point charge electric field looks like this, which we derived from Coulomb's law, substituting the integration of the voltage and assume that dl is nothing but dr dot ar. When you do so, this r, because this also can be written as ar, multiplied together will result in 1. You will be left with just dr. Then do the integration from b to a. You will find that all of these quantities just constant. Then you can take it outside the integration and don't forget the negative sign. And you have a simple integration from b to a of dr over r squared. Doing so will result in minus 1 over r. And substituting of the point AB, we can rewrite as Q over 4 by epsilon. This is the constant. Minus sign here multiplied by minus sign here will bring you 1. Then substitute by A, you will have 1 over RA minus 1 over RB, which is simply the potential difference between B and A. If you want just calculate the potential due single point, you can assume that the other point lies at infinity, means its R is very big. Then 1 over, if P was this, in this case P for example, 1 over infinity is nothing but 0. Then you can claim that V to a point is nothing but Q over 4 by epsilon RA. Now we move to calculation of electrostatic potential due to distributed charges. This is what we have reached in the previous slide due to a point charge. If we replace a point charge with a line of a charge, then a small quantity dV equal to nothing but dl multiplied by the charge density over 4 by epsilon r. Integrating this one will bring you V in this form. Likewise, you can do for the surface charge density and for the volume charge density, because in this case you have rho L, rho S ds, and in this case you have rho V d volume. In that case, this one you need to take double integral over the surface, and in this case you need to take derivative integral over the volume. And finally, you can reach these three nice equations. Now we are with one example, which is called electric dipole. Electric dipole is nothing but two identical charges with opposite sign, minus q and negative q. They are located at 2 points separated by distance d. And in this specific examples, we have the first charge located at 0, 0 and d over 2, and second charge located at b 0, 0 minus d over 2. And we are asked to calculate the potential at a point B very far from this. This means that R is much larger than D. To do so, we calculate the potential due to the first charge, VQ, which is Q over 4 by epsilon R1, where R is the distance between A and P. And then we calculate the potential due to V minus Q, which is nothing but minus Q over 4 by epsilon R2. And R2 is the distance or the vector between P and P. Summing these two will result in the equation here. Mathematical manipulation, you will find that this is nothing but Q over 4 by epsilon multiplied by R2 minus R1 over R1 multiplied by R2. Now we'll do some approximation. Assume with this assumption R is much larger than D, we can imagine that the 2 points actually are the same point. I mean A and B. If we assume so, this means R1 equal R2 equal R. But if we limit our assumption to this one, this will result that R2 minus R1 is equal to 0, which of course is not correct. So we redraw here, and if we assume this one is theta because they are parallel, also this one is original one is theta because this point is origin, and finally we also have this angle as theta. If we make a perpendicular here, we'll find there is a tiny difference between the two vectors r1 r2, which is this one. And if you make your calculation, you will find this small difference is nothing but the distance between them cosine theta, d cosine theta. So this is what I was explaining. Substituting with these values in this equation here, you will get that v is nothing but q over 4 by epsilon d cosine theta over r squared. And this, of course, assuming that r is much larger than d. If it was not the case, you need to use, of course, the equation, the original equation here. Thank you.